طيب, بسم الله الرحمن الرحيم. So last time we started to talk about just some simple motivation why mobile communication is an important topic, and we talked about various applications that we use in our daily life that sort of uses these technologies. Of course, nowadays with the proliferation of blockchain, and people are starting to think differently now. They are starting to think away from cloud, and so it's like we have an era of centralizing everything, and now we're going back to distributing everything. So it's like a transition phase now. So with edge computing and with blockchain, IoT, and all this stuff, we're going back to decentralizing everything. So this is a big transition. So personally, I have a personal view about this that will start to really discuss and leverage more communication issues when it comes to decentralized architectures. So today we're going to give a little bit of a history about mobile communications, when it started, and then we'll talk about the different generations. Of course, we started to signify, or we started to designate generations for mobile communication starting from 91 or something like this. So it was just recent. But actually, communication in general, communication especially through wireless in particular, started way back in ancient Greek history, and started like 150 BC when they started to just use the light from remote areas to just communicate just very simple words or simple signs. And of course, the start of the revolution regarding radio communication in general started with the Faraday and Maxwell and all these huge scientists who started to look into using radio waves, and we started to really put some specification on how electromagnetic waves actually work, what are the properties of electromagnetic waves that can travel through the air. And that was kind of the transition for starting to leverage any kind of radio communication or wireless communication. So in 1983, so this is like the ancient history, but in recent history or modern history, the first generation of the mobile communication or wireless communication started in 1983. So in 1983, we started to have the first kind of standard, like full-fledged standard of using wireless communication, and it was purely analog. So this is the AMPS, or the Advanced Mobile Phone Systems, and that was that actually started in the US. And that was pure analog communication. And what that means is this system allows us to transfer analog signals that represent, for example, our voice over the air. Okay, so dealing with analog signal is much easier. Why? Because digital signals, when we started to talk about digital signals, they look essentially like something like this. So digital signals, they have like a finite set of values, right? So in that case, it's easy for us to understand, and it's very good for us to use for analysis, right? For processing, because it represents ones and zeros, and we know that this is easier for us to process things. But to transfer this type of signal over any medium, not just wireless, this sharp transition tends to have infinite frequency components, right? And with that, it's very hard to represent the digital signal in ideal way over any type of medium, whether it's wired or wireless. So any medium will actually have some approximation of this digital signal. It's not going to have an ideal representation of a digital signal. Okay, so but our voice has like a normal analog form and it's easy to deal with that. We know how to generate this on any physical. It has like some limited range of frequencies. So we know that, for example, our voice in frequency ranges from what? Does anyone know? From 0 to 4K. Yeah, so very simple. So from 0 to 4K. This is in the low pass or baseband transmission. If we want to transfer it over wireless, then we have to use a like some kind of a broadband communication, which means that we shift it in the frequency. So it's fine. So we can start from any kind of frequency and shift by 4 kilohertz. So it's simple to deal with, right? Digital signals are a little bit hard. So that's why in the first generation, they started with pure analog communication. And for that, we used to be able to support only voice. So these walkie-talkies and stuff like that, to transfer voice, things like that, there was no data whatsoever. Data communication was not in the picture in any way, shape, or form. Okay? So thinking about digital signals representing binary bits, these kind of things did not exist in the first generation of wireless communication. Okay? So it's only in 1991 that we started digital type of wireless communication. By digital communication, we mean that we now want to be able to represent digital signals, okay, digital signals. Of course, we have to work around the fact that we have infinite frequency components and so on and so forth by having some approximations. We'll talk about this later. But in other words, dealing with digital signals was kind of a very important for us to be able to send data, text, and process things and so on and so forth. However, communicating these types of signals is somewhat tricky, and we'll have to deal with that. So the first standards came in 1991, and they historically, they also categorized this as G1, or first generation. And it's called DICT, or Digital Enhanced Cordless Telecommunication. So this was a European kind of standard. The American lasted for some time. So the US tends to be more market-driven. So if there is a need in the market about having any kind of standard, they would do it. Other than that, it's market-driven, which means that in addition to the standard, you may have many proprietary technologies out there. And in the past, especially in the US, they allowed this to happen. So in addition to amps, there were lots of other proprietary technologies which also dealt with analog communication other than amps. Okay? The European, they believed from early days, they believed more in the standard, in kind of a social system. Okay? So we have to follow certain unified standard. Okay? So from early days, the European, they tend to have standards that extend and they build on each other. So DICT standards, they worked in this range of frequency, and we'll talk about what this range implies in terms of properties of the wireless signal. So when you talk about certain frequency range, that entails certain properties on the wireless signal that we need to really understand and talk about. In terms of range, DICT focused on a range of 100 to 500 meters, which is pretty good. Well, it covers, a reasonable geographical area. But there was no like handover. Handover was not in the picture yet. So when you are in certain place, you communicate within this area. If you want to move to another place, you cannot seamlessly hand over from one place to another. Okay? So certainly your communication will be disconnected. When you go there, you will have to associate to another geographical area, but your communication is not preserved. Okay? Like what we have nowadays, we don't actually feel any type of disconnection or something. When we move from one location to another, the handover is seamless and we don't feel anything, right? So in these days, there was no such thing. There was no handover, and let alone, طبعا, there was no roaming all the fancy things that we have nowadays did not exist. But because it's digital communication, we started to have some type of a data communication. So in addition to the voice communication and so on, we started to also have some data transmission. So data transmission started to arise, started to be in the picture. And when we talk about 1.2 megabits per second, this is the collective data communication from 120 duplex channels. Okay? Of course, this is not for one user. So that tells you how hard was it, because nowadays this 1.2 megabits per second, one person can generate like sometimes 5 times this much. So there was some services like from the application layer, like voice encryption, authentication, and these kind of features started to be in place. Because when we talk about digital, these features become possible. In analog, what does it mean to have encryption in analog, in analog communication? It doesn't have any meaning. So encryption and all these things become significant or become valid only when we talk about digital data, right? It doesn't make any sense to talk about analog signal and it's encrypted. Analog is like continuous signal. There's no encryption with that. طيب. And in terms of density, there was like 10,000 users per kilometer, which is, so it's dense. So within a geographical area, you can cover 10,000 users per kilometer, which means that if you divide this 10,000, if you divide this aggregate data communication by 10,000 groups, so you can imagine how much data transmission can each user have. It's nothing, right? But that was a good start. And because of that, we have the services that we have nowadays. All right. So that was the end of generation 1. In generation 2 started about 1992, and we started to have the emergence of GSM, Global System for Mobile. And that's another standard that came from Europe, okay? And it's fully digital in that case, which means that we don't deal with analog signals as analog signals. We have to approximate analog signals using digital signals. So even voice, our voice, gets digitized. Okay, so forget about using any kind of analog communication. We started to deal with digital signals only. It started to work in the range of 900 megahertz. So that's for GSM in Europe. However, later on came other versions that worked in 800, sometimes above 1 gigahertz and so on. So there are multiple versions of GSM, especially GSM started to make a revolution in terms of wireless communication because it's purely digital communication, and everyone started to adopt it. Started in Europe, but later on spread all over the world and started to be the predominant kind of standard worldwide. Even in the US, they were kind of forced to leverage or to adopt different versions of GSM. And of course, the range of frequency here is kind of regulated by international bodies, as we will see later. So there are some international organizations that are responsible for assigning these frequency ranges to facilitate, like mutual interference, to facilitate handover, and for so many things. So, for example, here in Qatar now we have Ooredoo and we have Vodafone. So when they buy the license of using any spectrum or range of frequency, they have to get assigned different frequencies in order to avoid any kind of interference between the two networks. So that's handled by some regulations or some international regulation bodies. GSM also came with some automatic location, and the biggest feature was the support for handover. So that's actually what made GSM become the predominant kind of standard, because not only that, it supported roaming as well. So not only do you have a seamless handover when you move from one cell to another, but even when you move from one country to another, within Europe at least, it was possible and seamless. Okay? So if you drive, theoretically, if you drive through the border and have like some communication or some phone call, your phone call should not be disconnected. Of course, if you have the proper subscription. Okay? So, these features made GSM by far the predominant standards worldwide. طيب. In terms of services, there were support for data channels, separate data channels. Each would have 9.6 kilobits per second. Again, this is not in any way close to what we have nowadays, but it was, at that time, it was very good. So we can have like some fax services, so we can send some pages, we can have like voice calls even on data. That was kind of possible, but with some low quality. So that's for the second generation. In addition to that, or in parallel to this, we started to see the proliferation of wireless LANs. Kind of in parallel to this, we had the emergence of wireless LANs. So in 1997, we started to have the 802.11, the baseline standard, and later on, we had the B, and we had the G, later on we had the N, AC, and all of this. So the IEEE standard, it works on 2.4 gigahertz, unlike GSM, which, I mean, the early versions were in 900 megahertz, 800 megahertz, and so on. So this actually took the 2.4, which is what we call a ISM bands, industrial, I don't know, like industrial something, medical, something like that. It's unlicensed band, which means that if you manufacture any devices in this range of frequency, you don't have to pay money. So it's like a free frequency range that you can use. So in 1998, we started to have, pay attention to this, the specification of what we call UMTS. So UMTS is the specification that addresses what we call the IMT 2000 documents. And the IMT 2000, it's actually a requirement document, set of requirement documents, that they said that these are the abstract properties that we think should be part of next generation wireless communication, which is actually a set of requirements for 3G. So when we talk about these documents, 3G came later on, right? But that tells you that from 98 all the way to 2001, all of this was to develop the specifications and to work on prototypes and make sure that all the technologies related to 3G are up in place before you embark on 3G or you deploy 3G in actual networks. So it took maybe 4 years to do that. And that's what's happening now with 5G. So we live in 5G transition nowadays. So we have some prototypes and stuff, but we don't have wide deployment of 5G yet, okay? Because it's not standard. So any deployment for 5G is just a pilot test because it's not standardized yet. So the UMTS came to address the IMT 2000, which is the requirement documents for next generation wireless. And UMTS was the European proposal to address the IMT 2000. So that was kind of it's like when any organization says, this is a request for proposal. I need a proposal that addresses all these problems. Okay? So many people come up with proposals. So the UMTS was the European proposal to address the IMT 2000. Type. And I'm just giving you some important milestones in history that kind of give us some signs and some big stops in wireless communication. So in 1999, we started to have more variations of 802.11, starting with B and G and so on and so forth. So we started to have the 802.11b, which at that time supported 11 megabits per second. One thing to note here is that in the past, the wireless communication, including first generation and GSM, these are technologies that came to address first and foremost our voice communication. Okay, and they started to transition or to morph into data communication later on. So that was the philosophy. The main service was for voice communication, and then data communication will start to add on top of this. Wireless LANs came up with the reverse philosophy. So wireless LANs, when they first came about, the main target for wireless LANs was to support data communication. And later on, we started to use wireless LANs and so on and so forth for voice over IP and for other things. But the main target for wireless LANs was data communication. Because nowadays what we are finding is what we actually sometimes call convergence. So cellular communication started to support data communication, and wireless LANs started to support voice communication. So there is some kind of convergence. But in the past, the philosophy was always to design your technologies targeting one objective, which at that time, first generation, second generation, and as we will see, even 2.5G were mainly supporting voice communication with some data services. Okay, and wireless LANs support data communication with the possibility to use voice over IP later on. All right, so the IEEE 802.11b had a bandwidth or theoretical maximum throughput of 11 megabits per second. And at the same time, Bluetooth started to come into the picture for very short range communication, So the throughput at that time was less than 1 megabits per second. And of course, the decision about IMT came out, and they adopted the UMTS as one of the major standards to address the IMT 2000 and to be the next generation for wireless communication. However, that didn't come until 2001. Before that, we had what we call the 2.5G. 2.5G was, we want to have more data services on top of GSM. As we will study later on, GSM was built all types of ancient, if you will, wireless communication for voice. They would support circuit switched networks. Do you know the difference between circuit switched and packet switched? So for packet switch or circuit switched networks, we need to establish a virtual circuit end-to-end before we start communication. And this will help us to make sure that the voice communication is of high quality. And that's why when you make a phone call, first you have to dial the number, you have to wait for some time until the connection is established. Once the connection is established, in many cases, the voice quality would be very good. Why? Because the network has reserved some amount of resources for your voice call. Even if you call and you leave the phone aside, this circuit is still there. Okay? That's why we get charged by the second. For phone calls, we get charged by the second. When it comes to data communication, we get charged by the amount of data we send. Why? Because for voice communication, we have to use circuit switched networks. When we use circuit switched networks, we establish the communication, and the communication will keep being established even if you're not using anything. And for many people, this was inefficient. Okay? And that's why for data communication, usually circuit switched is not good, it's not efficient. So GSM was originally built based on the circuit switched concept. And that's why it was very good for voice communication. But for data communication, it's not efficient because we can send few bytes and then stop. It's not a long-term connection that we make a call and send voice back and forth, and it's just few bytes and I will turn off the communication. So it was not efficient at that time, right? So to have data services on top of GSM, we have to take one of two routes. One route is to say, okay, so let's start to augment circuit switched networks and tweak it to support data services. That's what happened here. So we started to have high-speed circuit switched data. High-speed circuit switched data. طبعا high speed is not high speed يعني. It's just at that time it was high speed, but nowadays of course it's not high speed. So circuit switched data. So this is just an emulation or tweaking for circuit switching GSM to support data services. Okay? And this tweak is supposed to minimize the cost of deployment because we don't have to change the entire hardware. We just need to change the network a little bit. So the upgrade was not that costly. Okay? So this was one school. يعني, to start to use the current technology with some added value or with some incremental enhancement. Okay? Another concept was the UMTS or 3G was a revolutionary school or revolutionary kind of approach, is that let's revamp the entire network and work on a completely packet switch networks. Given that in packet switch networks, we can customize it to work for voice. So of course, in that case, as a provider, as a network provider, in order to support 3G, you have to change your hardware significantly. So that's the difference between the two. That's why here, it was like, you support some data services, but it's not that significant. But in terms of cost of deployment, it's reasonable. So that's why they mark this as 2.5G. It's like a transition between second generation and third generation. Okay? So with third generation, it was completely a packet switch network. We started to have both packet switching and circuit switching working hand to hand. And in that case, we can support more data services with higher speed in addition to voice calls. I forgot to say here that GPRS was the early days of having packet switched connections over circuit switched networks. Okay? So, of course, as we will study later, GPRS, of course, we are, most of us are familiar with GPRS, at least we live the days of GPRS. We used it for data communication over 2G networks or over GSM. But again, the data rates that we used to have is extremely low compared to what we have nowadays. So 3G started to come into the picture in 2001. We started to have different standards of 3G. So at the same time when we had UMTS in Europe, we had CDMA 2000 we had a version in Korea, we had a version in the States. So CDMA 2000 was getting into the picture together with UMTS in the States. So in the States, they had their own standards. They always like to have their own solutions for everything. So there was like CDMA 2000 in the US, UMTS in Europe, and different versions like FOMA in Japan, and they have their own CDMA 2000 for Korea and so on and so forth. Okay? But all of them are 3G standards. And as we will see later, I'm not aware of anything that's an exception of this. All 3G standards are based on CDMA. So UMTS, CDMA 2000, FOMA, all these are based on CDMA. And we'll study CDMA and what it looks like, how it works, and so on and so forth. Okay? So GSM was built on FDMA, pure FDMA, and then 3G was based on CDMA, and we'll see the difference. And 4G nowadays, 4G is built on OFDMA, bravo عليك. Built on the OFDMA technology. So we'll study this when we talk about data link layer. We'll study these different things, and we'll see the difference between them. These are really fundamentals, very important fundamentals that we need to understand. Okay, so together with 3G, we had some, again, more adoption to wireless LAN. So again, cellular networks were booming, were proliferating for voice calls, as well as more added data services. Wireless LANs and hotspots started to also get widely available, mainly for data communication, but also possibly for providing some voice communication over these technologies or wireless LANs. But of course, wireless LANs is shorter in range. Of course, cellular communication is long range. So we had big towers and so on. In 2005, we started to have WiMAX. WiMAX at a certain point was perceived to be the killer for GSM technologies and for 3G and stuff. And then it died, like many other technologies. It almost died completely. And it lost ground completely to GSM technologies and to UMTS. Between 3G and 4G, similarly to 2.5G, we had some intermediary kind of technologies before 4G. So we had 3.5G technologies, which again, trying to have high-speed data connections and high-speed data communication on top of UMTS. So this means that we are always trying to enhance data communication. Okay, and of course this is motivated by the widespread applications that we have nowadays in the exchange of data and sensor technologies, where we have huge amount of data needs to be transferred and so on. So we're not really satisfied with the amount of throughput that we have, and we always need to have more data communication. So 3.5G, we started to have on top of UMTS. We started to have high-speed downlink packet access. Again, you don't have to memorize all these abbreviations. We'll get introduced to them later. But this technology is supposed to augment UMTS to work with higher data communication in the downlink. Yani download is fast, and upload is still the same. And of course, the motivation behind this is simple. This is more for consumers like ourselves. We like to download. We always work as clients, so we like to download very fast. But the upload is not that fast. So it's similar to ADSL, right? So this concept was always there. We like to have download speed much more than the upload speed. So this technology was targeting the download speed at least. Type. This one was UMTS, but with a high-speed downlink. ماشي? So that was the kind of the augmentation that we had. طيب. And we had also the high-speed uplink packet access. So this was more for servers and service providers and these kind of connections. So, but in both cases, the download speed or the upload speed was asymmetric, يعني was not similar, يعني. And then later on, we had what we call high-speed packet access, which supports both of them at the same time. And finally, in 2010, we started to have LTE. It stands for long-term evolution. So long-term evolution itself came with a whole new technology, which is OFDMA. So with OFDMA, we were able to send, we'll talk about it later, we were able to have higher spectral efficiency. يعني إيه ده هنتكلم. We started to have higher data rates in a very, very short frequency range. So that allowed us to have very high data rates in a short range of frequency. And we'll see how that happens. So with LTE, we started to see 4G, and nowadays we're starting to see 5G. So nobody knows exactly how 5G is going to look like eventually. We have some glimpse, but we don't know exactly how it will look like. ماشي? Sorry for taking so long, but any questions regarding this? What you need to know about this is actually this evolution of the different generations. Okay? You don't have to memorize all the abbreviations that I said now because we will go through them later. But at least in terms of milestones, you need to know exactly what happened in these milestones. يعني basically the text that we have on the slide. That you need to know about. ماشي? Any questions? طيب. That's not very important. This is part of the motivation. I don't know. I need to remove this slide because it's by now. I hope we are motivated enough to know that the proliferation and the increase of wireless communication in terms of users and subscribers and so on and so forth is going rapidly and exponentially. One thing to notice here is that fixed telephone lines here started to decrease, which is kind of interesting. And of course, we can feel it nowadays. Some of us, maybe 50% of us, don't have any landlines anymore. I still do, but some people, they don't have landlines. They don't actually deal with landlines anymore. So they use only cell phones and all the wireless devices. Other than that, everything else is increasing. Also, this slide is not, I think, is not 100% accurate anymore, because here we say that GSM is the predominant, but actually now we started to see more of a LTE kind of technology, and it's becoming more widely available. Maybe we should have like another LTE here, and it should be the same, if not maybe higher than GSM. But in the past, in the early past, maybe like 5 years back, this was quite valid, and GSM was by far the predominant technology worldwide. Okay. طيب. This is kind of important. So the areas of research when it comes to mobile communication, we have areas like transmission quality and spectral efficiency. And what that means is that for any transmission medium, we have available frequency range, okay, between like F1 and F2. And the idea of spectral efficiency is to try to have as much data as possible sent within this frequency range. Okay, so so in the past we used like harmonics to represent data signals and digital signals and so on and so forth. So we can use sine waves, Fourier, and so on. So we have some limitations when it comes to sending specific bit rate within this bandwidth. But later on with other types of technologies, especially that we have now multiple users, because if we have two users sending at the same time, all of us know that we have a, we always tell you if you have two users sending at the same time, what will happen? For Ethernet, مثلا, if we have two users sending at the same time, what happens? Collision. صح? That's what we keep telling you. That's not necessarily the case. If we have two nodes sending at the same time, but on two different frequencies, what will happen? Nothing. Right? So, so within this frequency range, if I can allocate like very, very small channels and kind of squeeze them and allow as many people as possible to send within this frequency range, then I can increase the amount of bit rate given this frequency range. And that's what we call a spectral efficiency. So in the same spectrum or frequency range, I need to send huge amount of data. And this is the sort of the fundamental technology behind the different generations. So CDMA talked about increasing spectral efficiency, and then OFDMA came with another concept that increased the spectral efficiency, especially when we leverage multiple users. Okay, so spectral efficiency is a very important area for mobile communication. Modulation. Modulation is, some of us are familiar with modulation. Modulation is the fact that we shift the signal in the frequency domain to have a non-zero frequency component. And this will allow us to have multiple channels and to allocate different communication to different channels. So this will allow us to have multiple communications going on concurrently, going on at the same time. ماشي? So modulation is a very important component, and there are multiple types of modulation. We have phase modulation, we have amplitude modulation, we have all these types of modulations that we will study later on. And we have coding, so we need to represent data into codes. And the reason is to enhance the error resistance and so on. Interference also, we'll talk about interference. So we'll talk about some of these areas a lot as part of this course. Radio resource management is a very important concept. When we have a big network معناها يعني we have multiple cell towers. Each cell tower has an amount of resources. And by resources we mean like channel, frequency range, time, okay, power. So these are resources. For us, these are resources. And radio resource management talks about the fact that we need to allocate these resources for different users in such a way that will achieve the highest utilization of my network. This is a very important concept. 90% of the research in data link layer in particular is about radio resource management. And we'll talk about this topic a lot as part of this course. Actually, in my group, we focus a lot on this. طيب. Also, mobility opens the door for other areas, like handover, location-dependent services. So we need to detect the location of the person, and based on detecting the location of the person, we need to provide customized services. So based on your location, I can send you specific information. So location-based services is another area of research. And also portability, which is more related to hardware design and to sometimes usability. When you want to have a small device to become portable, and that will entail the fact that your user interface needs to look in a specific way to handle the fact that you have a small display and so on. of course, will not cover this as part of the course in any way. And we'll touch a little bit on mobility, not that much, but we will focus mainly on this part. So we'll cover all these areas as part of the course. So this is the reference model for mobile communication. And when we tell you that it's wireless, in fact, this is partially like a lie, because it's not completely wireless, because from the mobile phone all the way to the tower, it's wireless. But the back end is mainly wired. Okay, so from the tower all the way to the server and to the office is 90% of the time is wired. Although now they use some kind of a microwave links and so on and so forth, but you need to have an infrastructure. But from the mobile phone to the tower is the wireless link. And in order to understand this easily, you can think of the tower as access point or a router, but in a bigger scale. So this tower will have three layers only. We'll have the physical layer, data link layer, and network layer. And we'll see the services and the issues that we need to worry about in each of these areas, okay, in terms of services. Any questions so far? Okay, so we'll talk about this and then we'll head to the prayer. Type. From the physical layer point of view, we touch on issues like frequency planning and frequency channels, and we'll talk about this. We'll talk about attenuation. In fact, very soon we'll talk about what attenuation means and so on. So these are issues that affect the properties of the analog signal or the digital signal that we deal with as part of the physical layer. And we have interference. We'll talk about interference a lot. And we'll have modulation. Modulation, as I said, shifting the frequency of the signal to allow for concurrent transmission. For data link layer, we're starting to deal with data. We're starting to deal with bits, or we're starting to deal with a frame, in which case this is the first layer when we can start to talk about any kind of encryption. Encryption deals with a binary data. And we also have medium access control. We talked about that a lot, as I think most of us, if not all of us, at least came across medium access control as part of undergrad or graduate courses before. So we know what medium access control means, and we'll touch on it and we'll study it in details again as part of this course, and we'll study different techniques as part of this course. And as I said, one of the very important things is radio resource management, which actually uses and leverages optimization techniques a lot. So we'll talk about optimization techniques a lot. So many of the resource management protocols and techniques, they like to formulate the resource management into an optimization problem, and then they solve the optimization problem. And that's what we do as part of our group. But the idea is how to do that in an efficient way, how to solve this optimization problem in an efficient way, and make sure that you have good optimization or the best solution for this problem. So we'll stop here. We'll have a 10-minute break, and then we'll come back. This topic is... Okay, so in Chapter 2, so this is the beginning of Chapter 2. In Chapter 2, we'll talk about wireless transmission frequencies for communication. It's very important now to talk about the properties of the wireless signal in different frequency ranges. So we need to understand really what's different about the wireless signal when we talk about specific frequency ranges. So in terms of frequency ranges, this line here shows the whole spectrum and the classification of the frequency ranges from very low frequency all the way to ultraviolet light. Okay, so very low frequency starts from 300 hertz, very, very extremely low. And for 300 hertz, we'll talk about a wavelength of 1 million meter. You know the wavelength of the signal? The wavelength of the signal is actually the distance that the signal travels in one cycle. يعني we'll talk about مثلا a periodic signal. Let's say مثلا sine wave. The sine wave has a specific duration. This is t. This is the duration or the cycle or the period of that periodic signal, right? Wavelength talks about the distance that this duration spans if we were to transfer this signal over a transmission medium, whether it's wireless or anything. So when we talk about a signal, when we talk about a distance is time times a speed. صح? So we have to know the speed. The speed here is the propagation speed, which ideally it's the speed of light. Okay, so the wavelength equals to t times the propagation speed, or c. Now, t, or the time duration, is the reverse of the frequency. So the frequency of this signal, when we talk about a periodic signal, the frequency of this signal is 1 over t, right? So t here is 1 over f. So this will convert to this equation here. So the wavelength is the speed of light divided by the frequency. In other words, both components, they are associated to each other through the speed of light. So yeah, they are equivalent in a way. So when I tell you a specific frequency, you should be able to get the wavelength. So that's why here, when we talk about 300 hertz, we talk about 1 million meter wavelength. If you multiply both, we get a speed of light, right? Because when we multiply 1 million meter, اللي هي 1 times 10 to the power 6 times 300. So it's 3 times 10 to the power 8, which is the speed of light. So if you multiply any of these components here, you get the speed of light. So it's constant. Okay? So from any one, you get the other. ماشي كده? Usually, we use frequencies all the way to light signals. When we get to light signals, we very commonly talk about wavelength. Okay, so very commonly we talk about, or we characterize light signals by wavelength. So when we get to these ranges here, layer optical transmission, we start to commonly use a wavelength. Below that, we commonly use frequency. But they are interchangeable through the speed of light. واضحة دي؟ طيب. Going back to the different frequency ranges. So we start from very low frequency. So we want to be able to characterize or get some idea about the properties of the wireless signal in each of these ranges. So first, when we talk about wired transmission or wired transmission medium, like twisted pair or coaxial cable, we talk about, as we said before, like baseband, when we talk about very, very low frequency components. So for twisted pair, we talk up to maybe actually less than even 3 megabits per second. Yani around 3 megabits per second at most. When we talk about coaxial cable, we talk about maybe 500 megahertz. Sorry, I said bits per second. No, I meant hertz. Here we talk about hertz. So twisted pair, we talk about 3 megahertz, versus coaxial cable, we may talk about a 500 megahertz. So the bandwidth of coaxial cable tends to be a little bit wider than twisted pair. Okay, that's why we use it for TV signal. Type. So the very low frequency ranges from 300 hertz all the way to 30 kilohertz. And in that range, we always use it, or we very commonly use it for submarine communication. We rarely use it for wireless communication, any of the wireless technologies that we talked about. So why is that? Well, one thing we need to look at is the very long wavelength. So the signal itself tends to have very, very long wavelength. So what does that mean? This means that the signal can have very, very long range. The signal itself can have very long range. And in fact, signals with very long wavelength, they tend to penetrate through any kind of obstacle. And that's why it's used for submarine communication. So it looks attractive, right? So it penetrates through any kind of obstacle. It's long-range signal, okay? So why not use it? Why not use it for our phones? تفضل.
You want to be able to reuse frequency very often in signal networks.
I can do that. I can do that within this range. I can divide it into smaller channels, and I can use it for concurrent communication. So that's still possible. The similar to what we do here, similar to what we do in 2.4 gigahertz or 5 gigahertz. We do the same, right? So we can divide this range of frequency into smaller channels, and we can use it for communication. So in fact, this will be very long range. It's nice. One thing that we'll talk about later is that, unfortunately, the size of the antenna is proportional to the wavelength. So that kills it. So imagine if you have an antenna with a length of 1 million meter. That's why we use it for submarine. We use it to communicate between submarines, because in submarines, you can have an antenna that's in the size of a building. That's possible, right? But for wideband communication or for a phone, it's not possible, right? So for very long wavelength signals, the antenna size is huge. So we cannot actually use it for, and that's why we use it for submarine communication mainly, but not in any type of broadband communication that we use nowadays.
Power is also, I think so, related to the wavelength.
Power?
So to transmit the signal of this low frequency, more power is required.
To transfer the signal in low frequency.
More
No, what happens? What you are saying is in a way correct. What happens is that if you transmit with a specific transmission power, the signal decays its power or attenuates its power inversely proportional to the frequency. Okay? Which means that if you have low frequency, the signal decays less. So which is good. That's why I said it's longer range. That's why I said that the signal will have longer range. Okay? And the fact that it penetrates through obstacles, you can use it for very, very, very long range communication. Like you can use it across Atlantic or something like this. Very long range. So they sometimes use it also for satellite communication. They use very large wavelength signals for sort of satellite communication, or because it penetrates through any obstacle. If you increase the frequency a little bit, the signal starts to reflect, start to reflect through certain obstacles, like the atmosphere. Okay, so if you increase a little bit towards the range of kilohertz and stuff like that, the signal itself starts to reflect from the atmosphere. So you can use it for relatively long range, but on Earth, not satellite communication. So in general, the higher the frequency, the faster the signal will decay its power, right? So the shorter the range. And also, any obstacle will affect the signal in terms of reflection and other things that we will talk about. There are very important phenomena that we talk about, shadowing and reflection and deflection and all of this, which all affect the wireless signal and impairs the wireless signal. We need to study that because that affects the properties of the wireless signal a lot. ماشي? So then we have the low frequency, medium frequency, high frequency, very high frequency, and stuff like that. So every range of these are used for example, radio communication. So for radio, for example, for AM, it tends to be in the order of a few megahertz, like in the low megahertz. FM, I think, uses like 88 megahertz, all the way to 108 or 108 megahertz. And again, this is considered low frequency, and that's why for FM and AM and these kind of things, it's still long range, right? That's why they use it for radio broadcast. So for radio, sometimes I'm not sure if you've tried it before, I used to drive across different states in the US or Canada, and I still listen to the same radio channel. I do it a lot. I like to do that. I like to drive across different provinces and different states and stuff, and I still listen to the same radio channel. So you drive for 3 hours and you're still listening to the same radio channel. So that's possible because it's very, very long range. Okay? And that's possible in low frequency. And for radio, again, because we're talking about low frequency, it still reflects from the atmosphere. So you can use it for on-Earth communication, right? You don't use it for satellite communication. And also, you would like to increase the frequency more in order to make the what did we talk about? The antenna size, in order to keep it a little bit small. So for AM and FM, we start to have the antenna size kind of it's still big, but it's smaller than submarine kind of communication, right? So the higher the frequency, the more and faster decay. The decay in terms of power, the shorter the range. But what's good is the antenna size is smaller. Okay? واضح? Okay. طيب. The other important property, as we said, the higher the frequency, the more reflections you have from this signal. So the signal tends to reflect a lot from different obstacles. And that's why in the very high frequency, we cannot have any kind of communication except line of sight. That's why we have line of sight communication. What line of sight communication means is that you have to have a direct beam, it's sort of a light, laser, like laser كده. Direct communication, line of sight. Because if you have any kind of omnidirectional, then it will reflect from here, and of course you have multiple copies of the wireless signal, and it will be very tricky to receive at the receiver. So that's why if you have, for very high frequency and very low wavelength, if you want to have efficient communication, you need to have a line of sight communication. So for wireless optical communication, they tend to have line of sight. Hatta for fiber optics, we design the fiber optics in such a way that mirrors and reflects the light and keep it within the fiber optic, right? But for wireless optical, so if you have a light that travels through the air, then your only way of having efficient communication is that if you have line of sight. Specific laser beams that have a line of sight. So this way, you can have efficient communication, and using the proper energy, you can have as much range as you want. ماشي؟ في حاجة صعبة؟ ماشي. So that it's interesting to know that يعني the higher the frequency is, there are some physical properties that affect the wireless signal, and that's why it affects the design of all our wireless devices, from antenna size, power, the size of the transceiver, all the techniques around it, whether we need modulation, we don't need modulation, and so on. Okay, I don't think there's any other thing that we need to talk about. Of course, we don't have to memorize the fact that ultra high frequency is from this to this. I don't memorize it myself. You don't have to really memorize all of this. You don't need to memorize this either. This is just to tell you that it's by no means an exhaustive list of the wireless standards, but the way that they have regulations for the different standards. So as you can see, you have for cellular phones, you have GSM in Europe, and you have the same version in the States, but this is called a GSM 880, and this is called 824, right? So it's just the regulation bodies, they kind of give different frequency ranges for different licenses or different carriers or different service providers, whether in Europe, the States, something like that. So you have different versions of GSM in different regions of the world. There is the UMTS, which is part of 3G. And again, you have versions in Europe, and you have different versions in the States. So, in the States in particular, you may have multiple, as we said, in the States, they tend to be more market-driven. So whatever the market requires, there are so many proprietary kind of deployments, and it's not unified, okay? Because it's federal, very large span of areas, and it's market-driven, it's capitalized, so it supports multiple solutions of the same technologies. Rather than in Europe, they tend to be more unified and have one standard for everyone. You had also the technologies, the wireless technologies for cordless phones, which do not necessarily require any kind of handover or roaming or this kind of things. You don't need to have that. So for this, we have the specialized standards for this in different regions, also for Europe, for the States, and for Japan, and so on. Wireless LANs, for some reason, tends to be unified worldwide. So all the wireless LAN standards, they are kind of unified worldwide. You may have different frequency ranges, although I see that some slightly different. Okay, so there are some differences in the frequency allocation, but still all of them, they follow the same standard. Okay, so these changes do not affect your compliance to the standard. You still have different frequency ranges, and you still abide by the standard or follow the same standard. Okay, طيب. So these are different standards. طيب. From now, we'll start to talk about the fundamental properties of a signal. And the fundamental parameters that affect the signal itself. So the simplest form of an analog signal is what we call a sine wave. This is the simplest form of an analog periodic signal. Why we talk about analog periodic signal first? Because the Fourier talked about the fact that we can represent any other composite signal using the simplest form of the sine wave. Okay, such that we can change 3 parameters. These are the parameters that we will talk about now. Does anyone know these parameters? تفضل.
Amplitude, frequency, phase.
Bravo. Yes. Those are the 3 fundamental parameters of any analog periodic signal. So amplitude. So the amplitude of the signal, the frequency, and the phase. Okay. طيب, in general, signals can be classified into continuous time or discrete time. And by that we mean that the signal itself can have, this is the time. If we assume that this is the time, the signal can have continuous values throughout the time. يعني it looks like something like this. Okay? Or discrete with respect to time. What does that mean? This means that you have value here, and then you have value here, and then you have value here, and then you have value here. So this is discrete with respect to time. There is also the concept of continuous value and discrete value. So here we're talking about a signal that looks like this. So you may have a signal that looks like it's continuous in time, but discrete in value. So you have the values here are discrete, which means that you have finite number of values. The signal takes predefined set of values. Okay? It's not continuous like this. Okay? Or it could be continuous like this one. So you can have continuous value but discrete time. صح? So you can have samples, but these samples, they take any value. So they are discrete in time but continuous in value. ماشي? So those are the four combinations of any signal. ماشي? So digital signals, when we say the word digital signals, by that we mean we have a discrete aspect, either in time or in value. Okay? And in both cases, we tend to have infinite frequency components in the frequency domain. يعني representing samples like this tends to have infinite frequency component. When we represent a change like this, we also tend to have infinite frequency components in the frequency domain. يعني the frequency in general measures the amount of change in the signal. So the one extreme is to have constant signal. This signal has no change. What is the frequency of this signal? Zero. صح? It doesn't have any change. Okay? When you have some change in the signal, then the signal will have some frequency. صح? If you have a sudden change like this, this is a very sudden change. This tends to have infinite frequency components. And it's important to understand, because the only way you can represent these types of signal is through a approximation. You can never have an idealistic representation over any medium for digital channel, for digital signals, For digital signals, it's impossible to have identical representation of any digital signal. You have to use approximation. ماشي؟ طيب. So the signal parameters of a periodic signal, we have the period or the time, and we have the frequency, and we have the phase. طيب. As we said, Fourier came up with a very important theory that any composite signal, whether it's periodic or non-periodic, whether it's digital or analog, it can be represented by multiple sine wave components with different amplitude, different frequency, and different phase. So you change the amplitude, you change the frequency, and you change the phase by having cosine. Cosine is sine, but with some phase shift. So you can have as many components as you want, and the more sine waves and cosine waves you have, the more accurate your representation will be for the original composite signal. And another amendment to this theory is to know that if the original signal is periodic, so you can have a periodic signal, any composite periodic signal, like مثلا you have كده, and this is repeated. So this is a periodic signal. It's a composite signal. It's not a sine wave. Okay? But it's periodic in the sense that you have a period that's repeated. Okay? So this periodic signal can be represented with finite number of sine waves. Finite, which means that in the frequency domain, you can represent this signal using discrete components. This is the frequency, and you can represent this periodic signal in the frequency domain using a discrete sample. Each of these is equivalent to one sine wave. Because we know that the sine wave has one frequency, صح? It's the simplest form, and it has one frequency. So in the frequency domain, we can represent the sine wave by one sample in the frequency domain. ماشي? We can represent one sine wave using one sample in the frequency domain, such that the amplitude of this is the amplitude of the signal. That's it. Okay? So if we have a composite signal, composite يعني مركبة يعني بالعربي يعني. Composite signal is like a complicated signal which is composed of multiple sine waves. If this composite signal is periodic, then the number of sine waves are finite or discrete like this. If this sine wave, if this composite signal is non-periodic, which means that it takes any form, non-periodic, then in the frequency domain, it will have a continuous representation of sine waves. Which means that ideally we can have infinite number of sine waves to represent the signal. Okay? Any questions? So, very commonly when we talk about digital signals like this, because we have different bit representations, this digital signal is almost never periodic. It's always non-periodic. Because you have different representations of the bits. So you have the 0, 1, 0, 1, 1, 0, 1. So you can almost never get this to be periodic. Which means that in the frequency domain, ideally, you would need to have infinite number of sine waves. ماشي? So it's a little bit hard, and that's why we tend to use some approximation to represent this type of digital signal. Okay? So it's what we are discussing is a little bit new for many. So if you are not following, please stop me and I can explain more. طيب. So we have different representations of the signal. We have, of course, the time domain. We have the frequency domain, and we are familiar with these two in a way, or at least some of us are familiar with the frequency domain. But we have another way of representing, which is phase diagrams, like this. Sometimes we call it the IQ diagram or the phase diagram. Okay? So the time gives us the shape of the signal or the different values in the time domain. The frequency focuses on the frequency components, but it doesn't show anything about the phases of the signal. Right? So the IQ or the phase diagram shows the phase as an angle in the IQ diagram. So basically, in the time domain, you have continuous signal. In the frequency, because this is a sine wave, so this example here shows a sine wave, and a sine wave has one frequency component, handles one frequency component in the frequency domain. Because the sine wave, again, is the simplest form of a periodic analog signal. There is no simpler than this. ماشي? So, in the frequency domain, we represent this sine wave by one sample in the frequency on a specific frequency. That's it. The IQ diagram or the phase diagram shows the phase. And this will become much clearer, and you will appreciate it more when you start to talk about constellations and things like that. We'll talk about this later. So this is the IQ diagram. So these are the different representations, and as we said, digital signals, they tend to have infinite frequencies for perfect transmission, and that's why we tend to use some approximation, as well as modulation, which we use to shift the signal in the frequency domain to provide lower broadband communication. So in baseband, what happens, baseband is used for Ethernet, for any type of wired cables. And it's guided communication, the line is dedicated, and that's it. So in that case, what we do is that the channel itself will have 0 frequency component up to specific frequency. So twisted pair, coaxial, all of them, they use the same baseband communication. So the signal will have low frequency component. Okay? And the channel itself will have a low pass filter behavior. Remember, هو low pass والband pass وكم? The channel will have a low pass filter behavior. So you will always have a 0 frequency component. For broadband, so what's good about this is that you can have low frequency components, low pass, only one frequency, and that's it. But the problem is that you need to have dedicated line to support this type of communication. Why? For dedicated line between 2 points, if you have two nodes are sending at the same time, this means that the 2 signals will overlap. So you're sending at the same time at the same frequency, because you always have 0 frequency components, right? So for baseband, if you have 2 nodes sending at the same time, they will overlap. And they will not they will be on top of each other. And that's why we keep telling you in Ethernet, if you have 2 nodes sending at the same time, collision will happen. This is not interference. This is collision, because they superimpose on each other. They completely overlap, because it's baseband communication. For modulation, facilitates what we call broadband communication, not baseband, broadband. By broadband, what we mean by that is that we can use modulation to shift the frequency for every node in the frequency domain. And instead of having from 0 to F1, it will be like from F1 to F2. And by changing that, you can have F3, F4, and you can have multiple channels. So you can have more than 2 nodes or 3 nodes sending at the same time with no collision. How? If they send on different frequency. Okay? Ethernet doesn't support this. This is supported in wireless a lot, of course. Anything else? Anything else you know about? Anything? Any other example that uses broadband communication? DSL uses broadband communication. So it's not only wireless. Even in wired communication, like DSL, we send data over telephone lines using this concept. So it's broadband. So we have to use modulation to shift the signal in the frequency domain. And this is what the modem does. The modem that we have for DSL, which is currently it's built inside the router. Anyway, so this uses the concept of modulation to facilitate broadband, to send data over telephone lines. Same thing. So any kind of multiple concurrent communication that we want to avoid the complete collision, we can use broadband communication. We can use modulation.
What about this coaxial? What they use for the TV signal? Multiple channels are also going on the same.
That's a good point. If you have multiple channels from a broadcast station, you can actually broadcast multiple TV channels using multiple frequencies. That's a perfect example. That's another broadband communication. That's a very good point. For TV, of course, it's broadcast. For radio, same thing. Okay, but this is wireless. We want to talk more about interesting examples even in wire. And also the concept of broadband communication is not exclusive to wireless. It's a concept. You want to send two signals at the same time with no overlap. So you use different frequency, as simple as that. And you do that by using modulation. ماشي? Any questions? When there are no questions, I feel like people are not, they are lost. يعني it will get worse. I don't know if I should start this. So when we talk about antennas is another interesting topic because electromagnetic waves, they tend to have specific patterns in the air that again affect the properties of the wireless signal. So the perfect type of antenna is to imagine that we have a small ball in the air and it has like a unified radiation of electromagnetic wave in all the three dimensions. It's like a sphere. So the electromagnetic the electromagnetic wave will be like a sphere. We don't have this in practice. We call this isotropic radiator. This is an idealistic type of antenna that we don't have. It's very hard to achieve in practice. Okay, you always have some kind of directionality of the magnetic wave. You always have this. You will never have a perfect sphere type of pattern to the electromagnetic wave. So nowadays we have other types of antennas. The common one is what we have on all types of Land Cruisers, اللي هو dipole antenna. This is the oldest type of practical type of antenna. So the dipole antenna looks like it has two forms. Either it gets fed from the bottom, and it has like a big post, or sometimes it has feeding from the middle. So the feeding point is in the middle. The most important property about this is to know that the length of this antenna is lambda over 2 to have efficient communication. That's what we talk about. Okay? So this length is proportional, the length of the antenna is proportional to the lambda over 2. And that's why we see people like spanning the antenna really high and to have efficient communication. So the lower the frequency, the higher the wavelength of the signal, and then the antenna size should be really high. Okay? So this dipole antenna tends to have a pattern that looks like this. Again, it's not, it tends to be like a circle from top. Okay? But from the side, it's not, it looks like it has like a kind of a very interesting shape. But it's not a sphere. It's not an isotropic. So it's not equal in all directions. So all types of antennas would have like a directional kind of effect. Some antennas, as I said, they get fed from the middle here, and they tend to have a specific shape. And if we look at this antenna from this side, we will see like sort of a sphere. So the electromagnetic wave will have a different pattern, but the actual spherical pattern is almost never achieved. It's idealistic case that we don't have. Type. Another interesting antenna pattern, it's called a sectorized antenna. A sectorized antenna is actually a series of a different, you have one antenna here, one antenna here, and one antenna here, and they form a composite antenna system. So you have antenna pattern in different directions. Could be like 3, could be 4, could be 6. Sometimes they do it like in a circle form. They call it circular antenna. So they call it 3-sector antenna, 6-sector antenna, or sometimes circular antenna. So it has like small antenna elements in a circle. So it gives you sort of a circle effect. The sectorized antennas is nothing but multiple antennas put as a series of antenna. And why we do this, we'll see later, that the size of each of these antenna is small, but why we have multiple antenna? This will give us more efficiency, as we will see later, because we can select between these antennas to enhance the efficiency of the received or the transmitted signal, as we will see in a minute. Okay, so by having multiple antennas, we can control which antenna receives what signal in order to increase the efficiency, and we'll see some effect of this. Okay. So this is the dipole antenna, except that we have multiple dipole antennas. So that this is 1 and this is 2. This is fed, as I said, this is fed from the bottom, and you have like a lambda over 4. If you feed it from the middle, then you have a lambda over 2. So if you feed it from the bottom, it's lambda over 4. If you feed it from the middle, you can have lambda over 4 here and lambda over 4 here. So you have a. So this is the largest type of antenna. So it's lambda over 2. If you have a series of these antennas together, also the distance between each 2 antennas should be also lambda over 2. You see? So that you have a distinct pattern from each antenna, and this is very important. Other than that, they will work effectively as one antenna. You won't be able to distinguish one from the other.
In that case, they will be in opposite phase.
In a?
Lambda by 2 distance means one will be like this, another will be like this.
Yes. So they can be sort of superimposed, and you can distinguish one from the other.
It will not nullify the effect of each other, because one is positive. It is not phase difference.
Yes. These are special diversity, not phase diversity.
Yes.
Okay. طيب. So multi-antenna element in general is a very important concept that will allow us to have the concept of what we call diversity. Diversity means that we have multiple antennas that we can use for the benefit of enhancing the efficiency of communication. How? One important class of categories is called switch diversity. Switch diversity means that we can select one antenna at a time. Okay? The antenna that gives us the highest reception power. Okay? So we have multiple antennas. So we can maximize the quality of reception by measuring the reception power between all the antennas and select the one with the highest power. Looks easy, and it increases the efficiency of reception. So the reception of the quality of the received signal will be maximized. So this way, the switch diversity is one of the important techniques that they use. It's very simple. You just go through the antennas and measure the power, and the one that gives you the maximum power, you activate it. You activate the reception from this antenna. It's very simple. There is the concept of diversity combining, which is what you referred to. So in that case, we will try to combine the output power of all of them at the same time, but we'll try to do it in such a way that they will be co-phase, not as you said, nullify each other. We'll try to keep them in phase so that the summation of all the power from all of them would would maximize the reception quality. Of course, this is more complicated. So to switch between the antennas, select one of them, it's easier. If you get the signal from all the antennas and start to do signal processing to co-phase them, that's more complicated. Okay? We will not get to the details of this. Don't worry about the signal processing aspect. We will not go through signal processing heavily as part of the course. But we'll talk about just some concepts. Here we're talking very high level about some concepts. We'll not get into intensive math or these kind of things. That's the concepts, high level. طيب فهو the properties about this lambda over 2, this is important because again this gives us an indication that when we increase the frequency, we reduce the wavelength and the size of the antenna gets reduced. So these are very important properties that we need to know about. Okay. This is the last slide before people sleep. Multiple input, multiple output, or MIMO. MIMO is a very important field of research, and we will not get to the details of this bardo in a very high level. It talks about all kind of signal processing on these multiple antennas in order to increase the reception quality and the efficiency of communication. And again, in a very high level, it tries to leverage the power of multiple antennas in order to receive a signal with a maximum possible quality or maximum possible properties. طبعا MIMO started to be used in 802.11n and started to be used heavily in LTE and all these things. So starting from these standards, MIMO has become a very fundamental component in all these standards. So the idea is very simple. So beamforming talks about the fact that from these antennas, you can imagine that you are sending one beam. Okay? So if we think about multiple antennas, and we try to send one beam from each. So imagine that if we send this beam in such a way that they will reach one point at the same time, then the effect at this point will be a maximum, right? What that means is that the signal at this point, all the signals, they will be co-phased, in which case the summation of all the three signals will multiply the amplitude of the signal, which means the power will be very high, right? When the power is very high, the reception quality will be the best. So what they try to do is that they try to control the phase at the sender side, okay, in order to make the signals reach at a certain point such that all the signals will be co-phased. They will have the same phase. So in that case, at this point, you will have the maximum quality or the maximum power. And by beamforming, we mean that we can play with the signal here in order to control where this happens. So we can control the location of this point where all the beams will meet each other at this point. So if we were to assume that T2 at the sender is T1 plus certain time difference, so instead of sending the signal at the same time, at the same amplitude, exactly at the same time, no. What happens is that we send this signal at time T1, and we send this signal at time T2 plus D2. And D2 is calculated using signal processing in such a way that at this point, they will meet each other at the exact same phase. So at this point, the summation of all the signals will be maximum. So this is what beamforming tries to achieve. And by changing this D2 and D3, we can control when this happens, where exactly this happens. So this means that in a wireless area, I can increase the coverage at certain points. So certain points in this geographical area would have very, very good quality reception. Okay? So I can control that. And I can control this dynamically. And that's what happens in 3G and 4G. You have an estimation of where the user is. And you can do some signal processing at the transmitter to maximize the quality of reception at this location. Because there is location estimation as part of the cellular system. So somehow I can get the location of the user, and I can maximize the reception quality at this location from the base station itself. مفهوم ولا بكلم؟ Again, we're talking very high level without getting into math. We're talking about concepts, very high level concepts. But I hope these concepts are easy to understand, because that's how complicated it gets as far as the course is concerned. It's just high level concepts that we need to understand. But understanding these concepts will allow you to really be able to evaluate and analyze and understand many of the standards that we have nowadays, because they are all built on top of all these simple concepts. Of course, implementing these concepts in reality is complicated. We will have to get into signal processing and intensive math. We don't want to do that. But in a high level, we need to at least understand the high level concept of these things. So this is what we call spatial multiplexing. So by spatial multiplexing here, we mean that, so beamforming tries to maximize the reception quality at certain points using the concept of MIMO, multiple antennas, sending the same signal, and they try to cooperatively, they try to maximize the reception quality at certain point. Okay. Another function of MIMO is what we call spatial multiplexing, in which case we split the high rate signal into multiple low rate streams. This is different from beamforming. Beamforming will try to send the same signal from all the antennas such that they meet at certain point. Spatial multiplexing, we know multiplexing. Multiplexing means that we multiplex multiple traffic, صح? So we do that from the antenna point of view by splitting the high data rate stream into multiple small or low rate streams. We send every low rate stream from multiple antennas, from different antennas. Okay? So in that case, we need to use all the antennas at the receiver, each to receive the stream from one antenna from the sender. And we call this spatial multiplexing. ماشي? So this is different from beamforming, because here we're sending multiple different streams. In beamforming, we're sending the same signal. مفهوم؟ مو الفرق؟ مفهوم الفرق؟ أيوة. Spatial refers to the fact that you send from different places, or different antenna.
Beamforming, they are sending from different antennas.
Yes, it still uses the concept of different places, but they're sending the same signal from different places. This is beamforming. Yes. Spatial multiplexing, they send different data streams from different antennas. Okay? So instead of sending the same signal, we break down the signal into 3 or 4 different low rate signals, and we send all of them from different antennas. And then at the receiver side, we receive either from one antenna or multiple antennas. It depends. So in that case, we can use multiple antenna at the sender, multiple antenna at the receiver. Or we can use multiple antenna at the sender and one antenna at the receiver.
What's the benefit
Of spatial, we increase the data rates, obviously. Instead of one antenna can send a signal with a specific frequency range, right? So this will allow you to send specific data rates. You have a limit of what data rate you can send, right?
It's
So by engaging all the 3 antennas to send different signals, you multiply the data rate by 3 or 4 or 5. يعني assuming that you have one antenna to send a specific wireless signal with a specific bandwidth. Using a specific bandwidth, there is a limit of how much data rate you can send within this bandwidth. صح ولا لا؟ صح؟ يعني it's logic. تمام؟ So if you have a specific range of bandwidth of the channel, then you are restricted of how much data rate you can send. If you have 3 antennas and they are decorrelated, which means that they are independent, so you can send different signals on different antennas such that you send 3 concurrent signals at the same time, at the same frequency, but they are in different places, using the special diversity.
But if the receiver has one antenna,
If the receiver has one antenna that supports very high bandwidth, it can. It can receive all of them. So it depends on the antenna properties at the receiver and the antenna properties of the sender. Maybe at the sender, you have a small form factor device like this. You can have multiple antennas, but all of them are small in size. So you can send specific data rate on each one. But you can engage all the 3 of them to send multiple data streams. At the receiver, you don't have this restriction. At the receiver, you have big antenna. It can receive with big bandwidths and so on. So you can have one antenna to serve all the antennas from here. It depends. If you have ad hoc communication between 2 devices that look like this, then you have to engage all the antennas from here and all the antennas from here to communicate. مفهوم? So at the receiver, it depends. You can engage one antenna or more, depending on the capabilities of this antenna. Because we said that depending on the frequency range, depending on the size of this antenna, it can receive wireless signal with a specific frequency range or bandwidth. So if your bandwidth is big, you can receive all the 3 signals all at the same time. Okay. You had a question?
No, for special multiplexing.
Special multiplexing, yeah.
Used for like speed up the signal.
Yeah, to increase the data rates. For special multiplexing, yes. And for beamforming, it's used to increase the reception quality. All of them, we call them different forms of diversity. Diversity, we mean that we use the concept of different antennas to enhance something, to improve something, whether it's to improve the reception quality or to improve the data rates. So you can increase the data rate of the stream by dividing it into 3 different antennas. Diversity coding, it's similar, but instead of sending signals on the 3 different antennas using different frequency or different phase or something, we send the 3 different signals using different codes. And we'll talk about CDMA and what this code means later on. You don't have to know the details about this now. Okay? But diversity in general is either through beamforming or special multiplexing. Beamforming talks about sending the same signal and controlling the phase of this signal such that they meet each other at a single point where the reception will be very much improved. Whereas special multiplexing always means mixing multiple streams. This is what we talked about in 455. Network is all about multiplexing, right? So the concept of multiplexing معناه mixing multiple streams. Okay, so that's the same concept. It's mixing multiple streams from multiple antennas, but these streams are actually a component of the same big stream. So we divide the high data stream into low data streams, into 2 or 3 or 4, and send these data streams from different antenna.
Doctor, can we interpret this small stream as a packet? That okay, a big.
I don't want to do that because I want to stick to the terminology that when we talk about bits and stream of bits, as I always teach my students in 455, when we talk about bits and stream of bits, we refer to a physical layer. When we talk about the concept of frames, we always mean a data link layer. When we talk about packets, we mean a network layer. So if you talk about packets at this level, you get confused. So I always want to stick to one terminology. When we talk about stream of bits, we talk about physical layer.
special multiplexing.
Mhm.
Is it one signal or multiple signals?
لا هم في كل الحالات هم multiple signals بس في حالة البيم forming هم multiple signals that represent the same bit stream. هو the same bit stream is sent from all the three antennas as identical signal, but they are a little bit shifted in phase so that they meet each other at certain point. يعني it's the same copy of the digital signal that I want to send that represent the same bit stream, but I send this same signal from the three antennas all at the same time. And I send them with some phase shift such that they meet each other at single point. In the special multiplexing, I get the original bit stream. First, I divide this big bit stream into smaller bit streams, 3 bit streams. If I combine these 3 bit streams, they will get me the original bit stream. Once I divide the bit stream into 3 different bit streams, I take each bit stream and then I send it as a signal over one antenna. And I send all the 3 of them at the same time. If they are separate from each other by lambda over 2, they will not affect each other in terms of interference or anything. That's why we said they have to be spaced carefully. ماشي? So I can send these 3 streams over the 3 antennas, and then I can receive all these streams at the receiver side, either using 1 antenna or 3 antenna, doesn't matter. So there is multiple input, single output. So there is a concept of MISO. And there is SIMO. And there is MIMO. يعني could be anything. So multiple input, single output. Multiple input, multiple output. Okay? So I can receive all the 3 streams on one antenna depending on the capability of this antenna. Okay? And then combine them at the receiver to get the original bit stream, which is high data rate. ماشي؟ واضح؟ طيب. طبعا we'll stop here before يعني people